Another important theorem related to derivatives is the squeeze theorem. Squeeze theorem. What does it say? Suppose you have a function. Suppose you have functions f, g, and h. Suppose f of a is equal to g of a is equal to h of a, and for all x, at least in some interval, we have, in, let us say, c to d, f of x is smaller than or equal to g of x is smaller than or equal to h of x, right? Also, f prime of a is equal to h prime of a is equal to h prime a. So maybe and also, but right. Then we have that g is differentiable at a, and f prime of a is equal to g prime of a is equal to h prime of a. Okay, so we don't need the interval, we just need some area around a where this is happening. So that's why we take this with, so a has to be in C, comma D. Okay, so we have this. The proof is relatively straightforward. Proof. Since f of x is smaller than or equal to g of x is smaller than or equal to h of x, f of x minus a is smaller than or equal to g of x minus a is smaller than or equal to h of x minus a, right? Therefore, limit x approaches a, f of x minus a over x minus a is smaller than or equal to limit x approaches a, g of x minus a over x minus a is smaller than or equal to limit x approaches a, h of x minus a over x minus a, right? And therefore I get that, well, f prime of a is smaller than or equal to g prime of a is smaller than or equal to h prime of a. But I know that f prime of a is equal to h prime of a, therefore f prime of a is equal to g prime of a is equal to h prime of a. Now, you might think this proof is completely fine, but there is a small mistake in what I have written, which is deliberate, but this need not always be true. This is true if x minus a is positive. If x minus a is negative, all these arrows get reversed, right? In that case, you would get exactly the same thing. F prime of a is greater than or equal to g prime of a, greater than or equal to h prime of a, and you'll still get these to be equal, so it doesn't change too much. But you have to keep in mind that if you are multiplying or dividing by something negative, it actually does flip the signs. Okay, so be careful. This proof does work out in both cases as long as you're careful with the signs, and that is fine. Okay, but why do we need to just stop at first derivatives? We know we can compute higher order derivatives in the same exact way, and so df over dx is our first derivative. Limit x goes to a, f of x plus h minus f of x minus f of a over x minus a And I can define the second derivative, d squared dx squared f, as the derivative of the first derivative. So f prime of x minus f prime of a, f prime of a over x minus a. Similarly, which we'll often denote by double dash at a, we can define higher derivatives as triple dash of a, quadruple dash of a, and the standard notation for these is f in bracket n at a, okay, which is equal to nth derivative dx to the n of f at x is equal to a, right? That's the proper Leibniz notation. We can also, instead of defining the derivative exactly at a, define what is called the symmetric derivative. A function is said to have a symmetric derivative at point A. A function f has symmetric derivative at a if f prime symmetric at a is equal to limit h goes to 0 f of a plus h minus f of a minus h all over 2h exists. Oops. Exists. Okay. Homework. Show that the symmetric derivative exists is equal to the normal derivative if the other one exists. But symmetric derivative might exist even without the normal derivative not existing. First, show that f prime s at x is equal to f prime at x if f prime x exists. Okay, but f prime s x can exist when f is not differentiable at x. Can exist when f is not differentiable at x. Okay,